Hey guys, welcome back to another episode of Making a Game with me. Let's build a tower defense game together. So today we're going to be working on the pathing of the AI, making them smarter with which path they choose. Just using an A-star search to find the best path with the least amount of resistance for them to go kill their end target. As you can see in the background, they're running straight to the target. But from going through 4 walls, because it's easier to break those 4 walls than to break the one big one. So we're going to be building something like this. Hope you guys enjoy. And yeah, so let's begin. First of all, I apologize if my voice is raspy. My wife and I had a shouting competition trying to see who can score the higher decibel. Not to flex, I got 129.7. She got 130.2, but who cares? Anyway, I'm not bitter, you're bitter. Let's start coding. So we're going to be doing the enemy movement, kind of intelligent movement script and like targeting system. So just before we start, there's a few things that we need to set up real quick. Over here I've set up a really simple scene. So all of these walls have the breakable tag. So just create a new tag called breakable, or whatever you really want, it doesn't matter. And all of them have the stats script from last time. The only difference is that we're going to be assigning each one of these walls a certain health, and from this health we're going to be deciding which wall to target for the enemies. So basically the idea is we want the enemies to go through the path of least resistance towards the target. Don't always go for the wall that's right in front of you, however go for the set of walls that makes the most sense. So the best example I give here is if these 4 walls are each 100 HP each, but this one is 500, the enemies should come from the side and go through these 4 walls, because that's the path of least resistance. And also it makes the enemy seem smarter, but it also gives the player strategic capabilities, so that later he can build the walls in a certain way that will make the enemies kind of funnel right through the path that the enemy would create, sorry, the player would create. So yeah, let's start. That's all the setup you really need. Just tag breakable and give them all the stats script. Alright, let's begin coding. That's the wrong window, my bad. Okay, so the first thing we need to do is actually fix something here on the stats. Right now each one of the controllers takes care of the death, but as I just mentioned, the walls don't have a controller. So I'm just gonna add a if statement here that will just check if the game object is breakable, and if it is, then we just set the object as inactive. So we don't delete the object, we just have it as inactive. Yeah, there you go. No, oops, there's one more thing missing. That will always set up inactive. And health is less than or equal to 0. Now when the health is less than or equal to 0 and the object is breakable, it will set it as inactive. That's all we really need for the stats script, so I'm just going to close it. Okay, next let's start working with the enemy controller itself. So the enemy controller is going to be it's going to have just certain changes, not that many. Just one thing that we do need to do is we need to set basically give the enemies a array of game objects, and then they go through them one by one. That will be like the set of targets they have to go through. So target 1, target 2, target 3, so on until the last target. That way we don't have to keep setting the target manually, right? So let's just create a public list of game objects, and I'm gonna call it targets. Okay, and then we need to actually start setting the targets, right? So let's create a new method in the update over here. So the check if target is valid, we're gonna just give it over here, right? So this needs to change a little bit. So if target is not active in hierarchy, then we win. That's good, but it won't work for us for now. So because we're changing it, right? There's more than one target. So let's just do this. So if the targets dot count is greater than 0 and the target is null, so there's no target but we do have targets, then we set the target to target 0. So basically pick the next target. Okay. And then here, if the target isn't active in hierarchy, that means the target died. So we need to check if the targets dot count is more than 0. So if there are some more targets, then we remove, targets, remove the target we currently have. And then when we remove the target, we need to set the new target to that. So basically, what this does is super simple. I think it's straightforward. I don't think I need to explain it. But let's do it anyways. So if this one just checks if there are targets, but our main target is null, then give it a target. However, if the target is not active in hierarchy, basically meaning that he's dead, then but the count is more than 0, so this we can actually put right next to it, because we don't need to have big nested loops, right? Like that. That looks much neater. Okay, so if the target isn't active in hierarchy and the target's count is more than 0, that means the target died. So we remove it from the list of targets and we feed to the next target in line, and then we return. Because we don't want to reach this line. And if this never runs, then they won. So basically, if there is a target, then we fetch it. If the target is not active in hierarchy and target count is greater than 0, then we return the target. So the check targets... Wait a minute, something's not right. Oh, right, sorry. So that we actually did need to keep it here. Sorry about that. So the reason this was here is because we want to know that if the target died, so if the target died and there are no more targets, then we won. Not the other way around. This will always trigger the previous one. So this is the correct way. Apologies. So if the target died, there are no more targets, then we win. If the target died, there are targets, then we remove the current target and give it the next one. Okay, I think we need to just drop this guy here as well. So this will always be running because we don't want to have cache, I guess. Okay, there you go. So if target died, then we remove the target. If there are no more targets, we celebrate. If there is a target, then we celebrate. Super simple. That's all for the enemy controller, really. We just wanted to create a new list for this stuff. And then in the simple spawner, we actually want to give it targets. We want to feed it the targets, right? So go.targets. This we will set right now in the wave config when we start working on it. But for now, just make sure you write this line. This is very important. I will remind you again at the end of the episode, so just keep that here. So next, let's talk about the enemy locomotion. There is a few things I decided to change here, just to make the enemies kind of run more, I guess, smoother. They run smoother and they don't jitter a lot. There was a problem previously where the enemies would jitter if they can't find the proper path, and this is a problem only with Unity 6, because I don't remember it being ever an issue. But I did find Llama Academy and they did teach Python Rock, which I will get into in a bit. So let's go over the modify changes, right? So let's just create a new vector 3. We will call it point to travel to. The reason is we don't want to, we're going to be creating a new point to travel to, which is going to be near the object, but not the object itself. Just because if you want to go to a wall and you send all of your enemies towards the wall and you give it the position of the wall, they will all pile up towards the middle of the wall. So we're going to create kind of a system for them to go to the closest point of the wall after being able to see the wall. Yeah, and then we're going to create a check timer that will check how often to, you know, refresh the point to travel to. Okay. And then now we need to do a bit of changes. So first let's create a bit of space here so it looks better. And we're no longer going to the target, but we're going to point to travel to, right? So point to travel to. And then there is nothing here, really. Okay, and that's correct. And then we're going to create a new method, which we're going to be calling update point to travel to. I know my naming is horrible, but bear with me, okay? And I'm going to feed the distance to target, which we're going to be starting to work on now. So, update point to travel to, we're going to go here, just under the set target. Actually, kind of want it to be about set target. Okay. Public void, update point to travel to. I know. Very, very creative name. But yeah. Okay. So now let's create a distance check real quick. So float distance check, which will be the distance between the target and our position. So this we will be using to check for the stopping distance, and this basically will create a. So sometimes they bug and they kind of stay a certain distance away from the wall. This check right here will fix that real quick. So sometimes they would keep going to the same target even though the target's already dead. So this, what it does is the point to travel to doesn't update. So this will just check if the target's already dead, or if the new target is too far away, it's moving. Go to it, don't just stand where you are, you know. So if the distance check is, so we're going to be creating kind of a range, right? So if it's greater than or equal to, if the distance to target is greater than or equal to distance check, and if it's greater than that, minus 7.5, and distance check is less than or equal to this is not right. It's supposed to be, okay, my bad. So it's this will never trigger. Weird. Okay, well, let's see how it works without them. We're gonna come back to them later. I think I was very tired when writing this, so I just messed it all up. So let's get back to this in a bit. Okay, other than that, let's start messing with the check timer. So check timer is greater than 0, or the distance to target is greater than the agent dot stopping distance. Then the check timer not equals time to time. Basically means just keep looping check timer to keep going. and return. We want to stop checking here. So if there is the so if the check timer is more than 0, then we keep reducing the check timer. And if the distance is less than the agent stopping distance, then we also return, because we don't want to keep checking for the new target. Okay. Yeah, so basically, to explain it better, it's to throttle the checking. I don't want them all to be checking all the time. That will cause frame issues. It will be overloading the game for no reason. Yeah. Okay. Now let's actually do the raycast hit. This will basically just check if we are within range and we can see our target, because I'll explain it in a second when we can see it. So physics, that's not how you spell physics. Physics dot raycast transform dot position, and then let's get the direction to the target. So it's target dot transform dot position minus transform dot position normalize. So this, what it does is it gets the direction to the target that we're looking at. So, and out hit, out hit, and then the range will be infinity. Yeah, I know, sorry. Okay, infinity. Alright. So basically, we only want to activate this when the enemy is within range. Not within range, sorry. When the enemy can see the wall or the target. So if the target is behind the wall, don't go to the nearest point, which is what we're going to be doing here. So if target dot get entity ID, which is a method, equals hit, sorry, the collider dot object dot ID. Yeah. Then we set the point to travel to be equals to the target dot game object dot collider. Sorry, that get component. Let's get component. Collider dot closest point, and then transform dot position. So let me explain this real quick. And then we also just check timer equals 1, and then return here. And if it all fails, then point to travel to. Traggle? I really wrote traggle? Okay, point to travel to equals target dot transform dot position. Let me rename it to travel. Maybe I named it traggle. Okay. Goody. So we check basically a raycast here every second. If the raycast can hit from our position towards the target and it hits the target itself that we're searching for, that means the target is within sight. We can see it. It's not behind a wall. It's not hidden or anything. We can see it. And then when we can see the target, then we set our travel to point to the closest point to the target. So if the wall is really wide and our enemy is running towards it, instead of going to the center of the wall at all times, go to the closest point to the enemy. That way all of the enemies don't pile up on top of each other, which is really good. Yeah, this would work perfectly like a charm. Like I really went through headaches just to be able to do that. But yeah. So next, I created a new pathing logic. So currently we just have this. This works, but it causes issues. which I'm going to be talking about in a bit. So let's create a new method called pathing logic. Pathing logic will be implemented down here. So let's create a public void pathing logic. So let's start. So basically, currently the enemies, when you whenever you set a destination, this one, if you do agent.destination and you give it a destination, it will this is an async function, which basically means it can run in the background while the script is running again. And what happens is it runs some checks to try to figure out if it's possible to go to the enemy or to go to the target or not. And when that is calculating, the agent sometimes twitches, so it's like it's not running as soon as you want, because the path sometimes is not found, but you're setting it to it. So he stops, but then the next frame he finds the path again, so he starts going, then he stops and starts going. And so every frame he stops, and every other frame he starts going. And that makes the enemy run and stop, then run and stop, then run and stop, and he never reaches his top speed, which is not good, because makes the enemy super weak and look weird, which we don't want. So let's create some checks here before setting the path, and we're going to be creating a new method which is called setPath. So first of all, we want to set redundant pathing. So if the point to travel to is currently the agent's destination, which means he does have the path already found, we don't want to search, right? So if the new point is not the current destination, then we check, but if it is, then we don't. So we avoid doing that check of can I go, can I not go, can I go, can I go. If you do that every frame, it's gonna first overload your CPU, secondly it's gonna cause the enemy to jitter, which we don't want. Okay, and then now we're going to be creating a vector3 new position, we're going to call it. It's going to be just equal to the point travel to, because we're going to be manipulating this variable, but we don't want to change the point to travel to. Okay, so now we need to do navmesh calculation. So just do if navmesh dot sample position, which is basically like check if we can go there or not. Sorry, sample position, what it does is it creates kind of like a small sphere around where you want to go to, and if any of that sphere around where you want to go to is a nav mesh, then we go there instead of going to the position itself, because sometimes that would cause an error, and then it would cause that there's no path to the thing because it's blocked, you know. So it's kind of the closest part to it. Okay, so then we want to go to point to travel to, and then out will be the nav mesh hit, which we're going to be calling hit. This basically stores the information of the new position. Math f max, sorry, math f dot max. Okay, dot max. We're going to be setting the target dot transform dot local scale dot y divided by 1.8 or 2. So I'll explain why I'm doing this. Let's explain this, sorry. So this here is kind of the grace that you want, and I figured that sometimes the wall is so high that you can't really set a certain value here. So what I found to be the best sweet spot is to get the scale for the wall divided by 1.8, and then if the wall is like massive, it will still have that radius be bigger, just so we can reach the ground, if that makes sense. So you don't want to have it to be too small that you will never be able to reach the ground. You don't have it to be too big that you'll always reach the ground. Makes sense? So you want the nearest point in the ground to be just within range, which is this is what it does. Okay, so if we found it, then we really don't need this, yeah? Then we just do new position equals hit dot position. Okay, that's if we found it. Then we set the new position. Then nav mesh path. So this will just gonna be assigning the path to the path that we're gonna want to go to, and then we're gonna create a quick check, right? Check, which we're gonna be equaling to nav mesh dot calculate path agent dot transform dot position, and then we're gonna be calling the agent dot area mask. Oops. So area mask, by the way, guys, is just which kind of nav mesh thing you want to go to, right? So for us, it's going to be the floor, which is the agent's going to be on, but this is a quick way to get it, and also out with the path. So the path will be set here. So if you can calculate the path and it's true, then the new path will be set, and then we can just do if check. Then we just set path. There we go. So this way we avoid the jittery and like having stuff run asynchronously. This will run perfect. It will never lag them, and everything will run smoothly, which we're going to be seeing in a bit. So honestly, visually, nothing changed. Literally nothing changed. I know this seems pointless, but trust me, it's very important. It will make the enemies run smoother. It's gonna make them, it's gonna reduce redundant checking, and it's gonna never make the enemy walk if he's gonna jitter, which is exactly what we want. Okay, we're done with the enemy locomotion. This should be sufficient. So let's go to the next one, which in the wave config, real quick. Let's start writing some what's it called, variables first. So one of the first variables we're gonna need to write is the scene variables, right? So who's the starting target, who's the end target. So I'm just gonna create it here. I'm gonna call it scene, and then public transform start, like where you want them to start, and public transform final target. So where you want them to start and where you want them to end. We're going to be setting start to default as the current target, the current object, but we're going to be doing that later. Okay, now there's a bunch of other stuff we need to write, which is gonna be a lot. So just quick thing. I have tried literally every single thing you can think of. I've tried. Oh, by the way, right now we're writing the script to find the best path to the turret. Okay, to the target. So I've tried every single method you can think of. I've tried finding the lowest HP walls. I've tried finding the path of least resistance using time. I've tried finding every single combination of walls towards a target and check which one has the least amount of HP combined. I've tried everything. And then I realized I'm trying to reinvent the wheel here, because I have studied in uni the A* search method, which is mainly used for maps. And I was thinking, why can't we just implement it here? And then I did, and it works perfectly, and I feel like an idiot because I wasted a whole week on this and delaying the video. But that's the price you pay for coding, right? At least for me, because I'm kind of an idiot sometimes. So let's actually start coding. So first, we need to create a kind of like a grid that we're gonna be using to traverse, right? So I'm gonna explain how it works later. So first of all, we're gonna be creating a auto fit arena boolean, which is gonna be defaulted by to true. And Next, we're going to be creating a vector 2. So we're basically changing it from 3D into 2D just to size. This is going to be setting to a random number. This will change when we fetch the AutoFit arena, don't worry. And then cell size, like how big is one cell, which right now just one, which is 1 meter by 1 meter, I think, which is how it works. I'm gonna explain it in a second. So then we're gonna create a arena padding. So just a bit of a pad, so from each side to have a bit bigger, just to contain the object. Okay, this will be mainly used to AutoFit arena. Sorry. Okay, so AutoFit arena is just going to be a boolean that does extra math for us, which we're going to be assigning down. When this is true, we want to fetch the arena size, and if it's not true, then we just get the arena size that we've set, which is 50 by 50. Cell size is how big is one cell, which is for us is going to be 1 by 1. And arena padding is just adding 2 to whatever is here, not for the manual one, but for the one that it auto fits for you. Next, we're going to just create let's create a header as well, since we're creating headers for everyone. I'm going to call it so gonna create a string of breakable tag, which I know ours is called breakable, but having a string will make it accessible through the inspector, which is nice. And then lastly, a header for the outputs, right? Which for us will be just a public list of game object, which is called targets, which is going to be a new list. This list of targets over here is the one we were referencing over here. So this should stop causing an error. Oh, why is it causing an error? Public list, it's public. Why? Why problem? Why is it causing an error? What did I do? Oh, oops, wave. Yeah, wave, because we're setting it wave here. Yeah, my bad. Wave the targets. Okay. And now we're done with this. Okay, now let's continue here. We have set up everything now for the stuff for the logic. We're gonna be creating a debug later to kind of make it look pretty. But for now, let's just start coding. This we can remove for now. Okay, now let's actually start coding from a clean slate. So the first thing we're gonna do, we're gonna create a class we're gonna call node. This will be used for internal pathfinding. The first one will be the first two, will be ints of x and y, basically the grid size, or the grid indices, and then vector 3 wall position. This is the position it is in the wall. I guess I don't need to explain this, but it's at the center of the cell. And then game object wall. This is to find the walls. And float, that's right. Okay. This is the accumulated cost of all of the walls, but right now we're setting it to the max value possible, just because we start with max and we start going all the way down. And then float h cost, which is basically just the heuristic hint, which is the short distance bias. We're going to talk about that later. I'm also going to include a video on a professor explaining how A-star searches work, because honestly I'm dumb and I don't know how to do it. I don't know how to explain it properly, but I do understand how it works. Trust me. So So this is, we're going to create a node parent, which is going to be a back pointer, which basically we can go back to if we want to. And public float f cost, which is equal to the g cost plus h cost. This is the heuristic, priority score. So you get the g cost plus h cost, and that gives you the priority score. Okay, now that's all that we need to do for the node. Next, let's start coding private node back of nodes, of grids, which is each grid, each position is a node basically. This is a 2D grid storage, and private int grid size x and grid size y. This is just the grid dimensions. Private vector 3 grid origin, which is the bottom left corner. It's the bottom left corner, not the center. Okay, bottom left is the origin because it's 0, 0. And then next is the list of nodes, which we're going to be calling the path node. Which is a new list of nodes. Okay, now we actually can start coding. I know this is a long setup, but trust me, this is how A-star works, and I'm not the one that designed this. If you have a problem, go pick it up with him. So let's create with the start method, which we're going to be just checking if the start transform is null. Then we just start transform. So, but this is what I was talking about earlier. If the start is empty, then we just set our transform, or the object's transform to the start. Okay. And then we're going to be doing the build grid, which will basically just build the map for us, and then run a star, which will run the A-star search for us. Okay, boy, this is a long script, guys. I know it's going to be a long video, but this is the best way to do this, and I'm sorry if I'm blabbering a lot. So let's actually start with the build grid first. Okay. So we're going to create a quick safety clamp. So if the cell size is less than or equal to, like, say, such a small number, this. Actually, that's a bit too many zeros. There you go. If it is, then cell size, we're going to be setting it to 1. Okay, this is a quick safety clamp just to make sure that cell sizes don't get insanely small. And so basically, you can adjust the cell size, and the smaller the cell size, the more accurate the pathing will be, but also the more expensive computationally it will be. So if it's 0, we will die. the PC will die. So just if it's super small, then set it to 1, so to avoid it being to avoid it crashing. I'd argue this is too many zeros as well, but I don't know what you guys want to do. And honestly, it doesn't matter the grid search and stuff like that, because it's going to find the path of least resistance in HP, and the enemy will do the rest, but this is good practice anyways. So now if there is an auto-fit arena, then we need to create the arena for it, which is going to be really easy. We're going to create a new function, which is going to be called auto, hey, stop doing that, auto-fit arena bounds, which we're going to create in a bit. So out grid origin, out grid size, and lastly out grid size again. Okay, let's create this method first before continuing. So private void auto fit arena bounds, which we're gonna have a out of vector 3, which is gonna be the origin, and out of int of size x, and then out outer end of size y. Okay. So now we need to feed the 3 outs. So let's start. Let's first of all start with the bounds of the start and goal kind of targets, right? So where we start and where we end, that will be the minimum bounds. So minimum x is math f dot whatever is the minimum between these two numbers. So start dot what I call it here, start transform dot position dot x, or the final target dot position dot x. So this is, we're trying to find which x is smaller, and then we want to do the maximum, the minimum for the z, and the maximum for the z. So max x min of z and max of z, which will just kind of alternate between these two. Just like that. Oh, but this has to be 0, sorry. There we go. So because we're doing 2D, we don't need y. So just x and z, because that makes the plane flat, basically. Okay, and then now let's fetch all the walls that we have, which will be just game object dot find game objects with an s with tag and breakable tag. Super simple. Okay. Now we need to loop for each one of those walls, and we get the component of collider. Then we're gonna start updating the min x and the max x and the min z and the max z. So basically what we're gonna do is try to fetch the maximum and minimum kind of arena by just fetching all of our walls. This is a very simple and cheap way of doing it, and I know I'm kind of cheesing it here, but it works really well, surprisingly. So for each wall and walls, I forgot that. For each wall and walls, we get a new collider. Yeah, and if there is no collider, then we continue. And then with RB, because collider bounds, and then we can just easily get the minimum of x from min x, which will basically equal to math f dot min again of min x, sorry, and b dot min dot x. There you go. Super simple. So we're just trying to search for where is the minimum x, where is the maximum x, and where is the minimum z, and where is the maximum z of all of them, basically. Like that. Oh, oops, max. There you go. Then max x. Then we change these from min to max, and this one also is max. There you go. So this basically finds us a grid of the minimum x and maximum x, no matter how tight it is. So it gets all of the walls and basically creates a little arena for us, and which later we can use as well if you want to kind of get the spawn of the enemies to be as close as possible to the arena. But yeah, but also we have padding, right, that we added. So min x minus equals arena padding, and max x minus plus equals arena padding, and the same thing with min z and max z. Okay, now we need to math f dot max of 1f or max x minus min x. So what this does is it converts world width and depth to the grid sizes, basically, which is the one that we have set earlier, which we're going to be setting now. So this is for width, and this one's for depth, which will be with z's instead of x's. So the minimum is going to be 1, and the maximum is whatever this is. So, and then size x is equal to math f dot max 1, or the math f dot ceil to int, which basically does ceiling, which is basically converts it to the integer number, which is always greater than or equal to the number that you give it, basically. So if it's 5.5, it will give you 6. If it's 6, it will give you 6. If it's 5.9, it will give you 6. If it's 5.01, it will also give you 6. So it always goes up, rounds up. Ceiling to int, we're gonna give it the width divided by the cell size. I know, guys, I'm talking a lot, but trust me, it's actually way simpler than all of this is kind of scary, but it's way simpler than it looks. So from width, we're gonna do depth for the y, which is technically z, by the way, but we're just changing it to x and y because that's how 2D works. And then we're gonna be also setting the origin to new vector 3 of minimum of x. Oops. So we want the lowest or the 0, 0 of this thing, right? So transform dot position dot y, it doesn't matter really. And lastly is the minimum of z. Oh, whoopsies. Okay, there you go. And that's it for this function, really. Now we can go back to continuing it. So if the autofit arena is enabled, then we autofit the bounds, which basically just gets the minimum and maximum of each one and sets its origin and size. That's it. Super simple stuff. Let's actually continue now. So else we just set the grid size according to the one that was given to us by our dear user. So it's kind of the same thing. Checking, can I get from here? Let's just get it from here. Simpler. Instead of size x, it will be grid size x, and grid size y. Instead of width and depth, it will be arena size dot x and arena size dot y. Okay, which does exactly as the columns and rows of it. So then we do grid origin as well, because we do have to set that. Just transform the position minus a new vector 3. That will be a arena size dot x and a 0 for the y because it doesn't matter. Arena size y. Now we're going to be multiplying it by a 0.5f. Let's get a smaller number for the bottom left. Okay. So this just creates an arena for us. Now let's actually start playing with the grids. Yippee! I love grids. Right, this is exhausting, isn't it? Okay, so okay, let's start. Let's create it for the grid. Get the new node, which is going to be the grids, these ones, which is the basically size and x and y to get all of the nodes in the grid basically. So we're going to create a node of size x and y to create the 2D grid that we're going to have. I'm sorry if I'm explaining this shit. Okay, and then we're going to also get all of the walls again. Here, game object dot find game objects with tag breakable tag. This is the walls that we're going to be setting on the grid. Okay. Now we're gonna need to start filling the grids. So we're gonna create a for loop on the X and the Y. We're gonna be looping over each X and go through every one of its Y's. Grid size X. Not grind, sorry. Grid size X. And X plus plus. So this goes over each X, and then we need to go over each Y. Like that. I love autocomplete. And then we're gonna get the world position. Called world pos. Index to world, which we're gonna be creating now. Don't worry. Okay. So we're gonna be creating this index to world, which will basically return the center of the cell in world space, which is super simple. Let's actually start creating it now. I don't think it will be more than like 4 lines of code, maybe 5. So I'm gonna create a new vector tree. I'm gonna call it index to world, and it will take in an int of X and an int of Y. Super simple stuff. Okay, so we're gonna be returning a new vector 3 of grid origin dot X plus the X plus 0.5 F, then we multiply it by the cell size. And the second variable is gonna be the Y, which is just, again, just the Y of the position. And lastly, we're gonna be feeding it the Z, which is, again, same thing. Actually, we can just copy and paste this. Why am I being a headache? E and Y. Again, Z is our second dimension here. We ignore Y. Z is the second one, and Y is the second one in 2 dimension. So this we're talking in 2D, and this we're talking in 3D, but converting it 2D. So this is technically in 3D. That's why we say Z, which is our 2D Y, and then we say Y here for our actual 2D Y, which we play this here. Super simple. I know it seems convoluted, but this makes sense, like mathematically. Okay, now let's continue. Now that we have our world position, we can continue to create the grid, right? So we're going through each one of the Y and X's. We're gonna get the node now. So node is a new node, and let's feed it the information that we need. So the X is an X, so the Y is a Y, the world position is world position, okay. And the wall is nothing. Okay, simple node. And then let's create. So now we need to feed, so basically set the wall to be, now we're gonna loop over each wall and check if the wall crosses the node, and if the node is a part of the wall, then we're gonna feed that node and make it part of, feed the wall into the node. That way we know that in that node there's a wall. So for each wall and walls, we check, first of all we get the collider of the wall, get component collider, yep, and if the collider and collider.bounds contains wall position, so that means if the wall position if the wall's position ends within the boundaries, so if this node is in the boundaries, we set the wall of in the node there, and then we break because we don't need to search more. And yeah, then we have to store the node, which means after our for each loop here, we just do grid. That way we save the node. And you can see this is how we map, basically go over each single position in the grid that's like in the floor. So basically here, if I go back to Unity, I can show you. So here we can just do a super simple example. You guys can see each one of these boxes. So each one of these boxes, we can kind of see it as a node, right? So what we're doing is we're finding the furthest most point, which is here, and the furthest most point in the other side. So this is it, and then we spawn over there, so it extends all the way there. And then everything in this square, like each one of these little squares, is a new node. So this way we fill in all of the nodes, and basically if a node corresponds with a wall, like here, it sets this wall to that node. That way we can do a search that goes through each one of the nodes to see if which path is the best. This is the best way to really explain it. I hope you understood that. This is super simple, really. So let's just keep going. So we finished the build grid, which works perfectly. Now we have our grid. Let's actually run the A star method, which will get the actual path that we need to take. So, damn, I need water. Okay, so let's create a new run A star method, which will actually run the search. I'm gonna set the node start node, which is where we start. So, oops. And we're gonna create wall to node method, and we're gonna be giving it the start transform. The position of the start transform, and we're gonna give it actually clamp to grid to be true. So we're going to create this now, this method. That will just get us our start node and our end goal node, which will be the same thing, but instead of start transform, we're going to do final target. Okay, now let's actually create this method. So wall to node is going to be quite a lengthy method, but it's actually kind of straightforward. So let me show you. This basically gets the position of the node, basically according to the world. So I'm gonna give it a vector 3 world position. Actually, let's keep it small. World position and boolean clamp to grid. Oh, whoops! It's actually gonna return a node. My bad. There you go. Okay. Let's start working on it. So the first float, which is going to be our x, is going to be... So here we're going to just convert our world position basically into the grid kind of what's it called? That size. Sorry. Grid. I don't know why I keep writing grind. So we're converting the world position to the grid indices, so that way we can like kind of find where the position is in our grid. So we're gonna do the same with x and z, which is the derivative of them. The world position of z. Same thing here. Oops. Yep, that's perfect. Okay, now we get the ix of map f, which is gonna floor it, and then the iy, which is the column index and the row index here, which is gonna be this tc. Okay, now here let's create a quick handle for if something is out of bounds, because we don't want it to die on us. iy, oops, or the ix is greater than or equal to the grid size x, or the iy is greater than or equal to grid size y. So this handles anything that's out of bounds. Oops, what? Okay. Now, if there is no clamp to grid, I actually wrote it clamp to grind. Are you kidding me? Clamp to grid. What's wrong with me and grind? Clamp to grid. There you go. Okay. So if it isn't, then we just return. But that basically means if we don't want to clamp it to the grid, which basically means if it's out of bounds, then bring it to the closest point in the grid, then we just return it. And if we do want to clip it, then just an ix equals mathf dot clamp. We have this amazing function which will basically give us a clamp on nearest valid cell, basically, which is gonna be the grid size x minus 1, and then the same thing for the y, but we're gonna be setting it to y and y. There you go. So this just clamps it, and if it is not out of bounds, then we just return a grid ix and y. So this is super simple. So what we do is we convert the world position to the grid indices here, and then we get the column in indices for the x and y using the float int. Basically, float int basically is opposite of ceiling, so whatever number you get decimal will always be floored to the number under it. So 5.5 will always be 5, 5.9999 will be 5 as well. It doesn't matter. And then we check if this position is outside of the kind of clamp, so outside of the cell or out of bounds. And if it is, then we clamp it if clamping is enabled, which I have it here. And then we just return it, clamped or not clamped if it's in bounds. Super simple. And yeah, so now we can continue working on the A star search. Again, I'm so sorry guys, this episode's gonna be long. So if the start node is null, or the goal node is null, then we want to return, because we don't want it to do anything there. Because yeah, there is no nodes, so it's out of bounds, so we don't want it to run the search, because that will break it. Okay, so now we need to reset each one of the nodes variable n in grid. So let's reset each one of the nodes with cost and everything, and dot cost equals float dot max value, and then n dot h cost equals 0, which is basically nothing, and then they don't have parents, so null. Okay, so this is just resetting in case you want to run it more than once, but I don't see why you would do that, because this would only run at the start, I think. But it's always good to do that. Okay. Now we have the frontier node, which is our open node. Okay. And then the visited nodes, or the closed nodes, which actually isn't a set, a list, sorry, it's a hash set. And then the start node dot g cost, we're going to be setting to 0, so that's where we're starting. And then the start node h cost will equal to heuristic start node, and goal node. So heuristic is a method that we're gonna write now, and it just gets the smallest distance bias between so that the A star can explore forward. And it's super simple. it just gets a method. So it just gets the distance. So we're gonna create a private float heuristic here of node A and node B. And it's just a one line. So we return the vector 3 dot distance of the A world position and B world position. And we multiply it by 0.01f. So this is super simple. It just gets the distance bias so that our A star function can move forward. Yeah, so let's continue. The A star over here. After we get the heuristic, we need to feed the node into the open node. So we do open.add start node, and basically that's the seed frontier that we're gonna feed it. And then while open count is greater than 0, that means we do have 1. Then we get the node current equals lowest f open. So lowest f, we're gonna be creating it now. It just gets the lowest possible f value, and it's a super simple method again. It's created right here, and this is how I like to code. I like to split up everything. I don't want to have everything be in one method. That way you kind of get lost. So let's actually just call it list here. Okay, so the best node will be basically the first one always. So, but we're also gonna loop over each one of them except the first one. So int I1, I plus, and then we just check if the current one's f cost is better than the current best cost. And we just do this, and then we return best. It's super simple. It gets the best f cost. I don't think this method can get any simpler than this, but yeah. So yeah, so we get the lowest f, which is basically the lowest heuristic value. And where's the ISO? I lost it. Oh, it's here. Sorry. So we get the lowest f, and then we remove the current one. Let's remove current, which is the one with the lowest f, and then closed we add the current, which is our final one. And then if current is the goal node, then we do get the path nodes equals reconstruct path to the goal node. So reconstruct path is another method we're writing. Yippee, one more method. Oh boy, methods. I love them a lot. By the way, guys, this is like I think it's like about 280 lines of code. So we're almost done. Don't worry, we're getting there. So list of nodes, reconstruct path, and then the node will be called goal node. There you go. So this will just basically set kind of going from the node, which is our goal, all the way back to the start node by just keep getting the parents that we have set earlier. We haven't set yet, but we're going to be setting. We're going to keep getting the parents, and that will be the path, the most optimal path, basically. So a new path variable, and I'm going to be calling it node C equals the goal node, which is our current node. So while C does not equal null, which means that while there is a parent, then we just keep going. Don't know why it's saying this. Okay, so there is a parent. Then we just do parent path.add this current one, and then we set the current one to be the current one's parent. So it just keeps getting the parent and keeps going up until it finds the one without the parent, which is our start node. Path.reverse. There you go. And then return path. So this just flips the path. So instead of going from end to start, we'll go from start to end. So this really makes this is super simple, which I think I can explain it easier in Unity again. So let's say this turret over here is our end goal. As soon as it finds it, it goes like, oh, so we're here. Which one? This is the node. Which one is the parent? It's this one. Which one is his parent? It's this one. And it keeps going back and back and back and back and back and back until it reaches this one. It says which one is the parent? It's nothing. That means this is the list, which is a straight line. And then because it's going from left to right, it reverses it, so it goes from right to left, which is the start to end. Super simple. Reconstruct path, which did I misspell it? Reconstruct path. Oh, there is no U. Reconstruct. Okay. There you go. Yeah, that's if we basically find the target, which is like find basically the current target is the goal target, and then we extract the targets, which is a super simple method. I'm gonna show you how it works, which is, yay guys, another method. Look at that. Right, so let's actually create this private void extract targets, which is gonna do targets.clear. So basically we wanna empty up the targets, which is the one that actually is gonna be fed into the enemy. And then we're gonna create a new hash set of game objects, which is called scene. And then for each variable n in path nodes, for each node in the nodes, basically, that's our final node, our final path nodes. If the n dot wall, like basically if it has a wall, and scene dot add n dot wall. So basically, if it has a wall and it hasn't been added, then we get the targets dot add and dot wall. So we add it to the scene, and this basically checks if it has been added. If not, then it adds it to the scene and then adds it to the targets. Super simple stuff. And then finally, after we finish adding all of the targets, we do targets add the final target, which is a game object. No, it's not. That's a yep. There you go. Which basically it adds all of the walls into a list that's into our targets list, and then at the end it will add our final target, which is the one we're actually going to attack. So this is what happens when we do find the path. However, how do we start finding the path? Let's actually start talking about that, which is super simple. At least I think it's super simple. So we're gonna go to, for each of the variable, we're gonna call them neighbors. So for each neighbor, in get neighbors, which, guess what, guys? It's another method we're gonna write. Okay, so get neighbors is super simple. What it's gonna do is it's gonna enumerate. So it's an enumerable of node get neighbors and then node. I'm getting lazy at this point. All it's gonna do is gonna get exactly our current node's position, and then find each one of his neighbors of each, like in each direction. So we're gonna need to create a deltas basically. So an int of size deltas equals super simple. So 1 0, then -1 and 0, then 0 and 1, and then 0 and -1. So this basically just gets, so this goes up, this goes down, this goes right, and this goes left. Sorry, this goes, yeah, right, and this goes left. I think? Yeah, I mean, it depends on where it is. It doesn't matter. So let's go over each one of the deltas. And just get it new into nx, which is equals to the node x plus deltas of the I0. And then for the y, it's the, sorry, what am I doing? That. So if nx, this is basically checking for valid neighbors, and y, make sure they're not out of bounds or anything. I really hope my mic is on. It'd suck if it isn't. Back with the grinds. Grid size x, and ny is grid size y. Whoops, it's nx is that. Then yield the return grids of nx and ny. Super simple stuff. So it gets the neighbor basically. Okay. And then let's continue. So for each neighbor and the neighbors, we wanna first check if the neighbor does exist. So if the closed dot contains neighbor, that means we've already been there. So continue basically. And then float step cost, which is most cost step, which is going to be 0 for now. But if there is a wall, then the variable s equals, which is the stats of neighbor.wall.get component, which we have stats. So it will basically get the wall stats and set that to be our step cost. So step cost equals s f. This is just to check basically if the wall does have HP and it's more than 0 basically. Because if it's more than 0, then use it. If it's less than 0, then just turn it into 0. Okay. And then float tentative g current g cost plus step cost. Basically, this is the new path cost to the neighbor. So how much cost to go to our neighbor? And then if the tentative g is is less than the g cost of the neighbor, that means we found a cheaper route, and we're gonna be taking, oops, this seems duplicated. That means we found a cheaper route and we want to take that route. So neighbor dot parent equals current, and neighbor dot g cost equals tentative, and neighbor dot h cost equals heuristic, which is the method we created earlier, neighbor and goal node. So how far is how much it costs to get to the goal node, and open dot contains neighbor. If it doesn't contain neighbor, then open the add neighbor. So it checks if the cost is cheap. If it is cheaper than it is, then we set it as our next node because it's the cheapest, and we set our current node to be its parent. So we were where we were basically, and I think that's it. That's how that works. That was really long, but okay, I actually did misplace some things, so let's just fix them one by one. So first one is an auto fit area bounds. I actually did not mean to do all men here. This is wrong. So it's supposed to be the max x supposed to use max number x, and then the max z as well is supposed to be use max z. Oops, this is max. Oopsies. Like that. It's supposed to be min max like that. I accidentally kept them all as a min, which is incorrect. Next one is in run a star, which is up here. Where is it? Here. I accidentally said g cost twice here, which is incorrect. So g cost is supposed to be 0. H cost is supposed to be heuristic. Right. That's now correct. And lastly, in get neighbors, I have an error too. I have accidentally set both of them to node x. It's supposed to be node x and node y here. Oop, another thing also, I forgot to change these to Z. Oh my god, I'm so tired. But yeah, I think this is all of the differences. And now let's actually see if it works or not. Go, start. Yep, that's perfect. You can see they're all running. They're gonna go through the path of the least resistance, which is these 4, which add up to 400 in total. And you can see as soon as they run, they go for it. And you can see how here they're lagging, kind of just standing there doing nothing. That's where this code bit that I commented out earlier comes in hand, which is in the locomotion. Oh, it's not here. I think I closed the thing. So it's in project. Where's locomotion? Here. This bit. That's what it does. So it basically does a quick check of the distance, and if the distance between the target and the distance between the enemy, so basically the distance to target, which is the 0.2 that they have to go to, and the distance between him and the target, so the actual distance and the distance between the go to, if they're too big, so basically the point we're traveling to and the point that the enemy is, the target is, sorry, okay, let me just say it one more time. So where the target is and where we're going to, if they're too far apart, then get the new target or just go to the center of the target. At that point we don't care because the target is just too far out of reach, and we don't want it to be that far out of reach when we're hitting it. So if the edge of the wall is too far, then just make him get closer to the center of the wall, is basically what this bit does. So it checks the distance between the target and the transform, and this one checks the distance between the target and the move to, which is set to be the where is it? It's set to be the closest point of the collider. So here we just do greater than or equals the distance check greater than plus 7.5 f. There you go. So that way, if it's in this range, then it's sorry, if it's outside this range, so we add a, if it's not in the range that we're defining, Then we set the point to travel to be equals to the target dot transform the position. There you go. This is an easier way to do it. Just basically checks if the target point he wants to go to is too far from the actual enemy, then just set the new point to go to be the enemy. That's it. So now let's check if this works. They should all start running here. They start looping and instantly go around. Yep, perfect. And you see some of them will go head towards the center, which is exactly how I want it to be. There you go. Perfect. One small thing that you guys might have noticed is they actually don't face the area they're attacking, but they rather face the center of the target when they're attacking, which is not good. So over here where we have face target, instead of using this target position, just give it the point of target. Now it should look smoother. So that's pretty much all. So now we can do some testing. You can see if we set this to be 401, which is just 1 HP more than all of this, they should run around it. Like that. They're running around it to go through the path of least resistance. Just because this is 1 HP more. As soon as they go around and they can see the wall, they start running towards it. There you go. That is so much smoother than it used to be. There you go. But if we set it to be 399, so 1 less than the path, then they should go through it. There you go. They're going through it rather than around it. Yeah. And you saw that weird movement that they're doing? That's here. We're setting it here. So the distance here is kind of a bit big. So we can just call it range buffer, which you can tweak this number. I haven't really tweaked it or played with it. I just kind of got tired, so I just used 7.5 as base. But yeah, you can use a range buffer, which you could also do it as like the distance width or whatever. Anyways, doesn't matter. You can play with it, but you saw it functionally working. If it's just under, and I think if it's 400, then it picks the one that has the least amount of targets, so it should go straight through. Nope, it prefers this one. So yeah, that's all. I'm so sorry for the really long episode. I hope you guys enjoyed. I really blabbered a lot. My throat hurts and I need to go sleep. It was fun talking about all of this. I hope you guys enjoyed. If you have any comments or questions, please drop them below or join Discord. I'm always available there. And yeah, thank you guys for watching. Catch you in the next one. See ya.